Okay, everyone, we're back with another module, and this time we're going to talk about how we can scale OSPF over hub-spoke networks. In the context of our business, named SBC, they're expanding into production operations. They've leased some new floor space in a factory, and this is where they're going to actually manufacture the products that they sell. We'll handle the factory design soon, but in the meantime, they're standing up some retail stores as an outlet to sell their products. They've got an MPLS Layer 3 VPN transport network to connect all these sites, but they still want to have their own internal WAN over the top. They want to continue using OSPF so they don't have to introduce any new routing protocols and don't have to deal with redistribution. Ultimately, they're going to have thousands of stores, so we need something to scale, and we additionally want to have spoke-to-spoke connectivity along with that scaling. Before we explain how the solution works, let's generally understand why OSPF is generally a poor choice in any hub-spoke network. The problem with link state protocols in general is that every router within a flooding domain, or in the case of OSPF, an area, all have the same view of the topology. The idea is that the routers will flood their LSAs, and each router will say, okay, I have all the LSAs for all the devices and prefixes and DRs in the network. Now I need to build a topological graph so I can find out how to navigate through. This sounds like a good idea, and it is in a lot of networks, but it doesn't work well over hub-spoke because all the spokes need to learn about all the other spokes. There are some ways to carve up the network into different areas. So for example, if you had 1,000 sites, maybe you do 10 areas with each area containing 100 sites. That is one scaling technique, but it's really not dynamic and it's not that effective. I also think it's useful to go through a brief thought exercise using EIGRP over WAN instead of OSPF. If we were allowed to use EIGRP here, I definitely would, because there's two big advantages you should know about. The first thing we can do is we can configure the routers as stub routers. These routers can never be queried, they'll only advertise their connected networks, and they're not used for transit generally speaking. That means that when there are changes in the network, the hub can never ask the spoke what the prefixes are or how to get to any other node. We can also prevent upstream queries from the spoke to the hub by doing hub-level summarization. This allows the hub to push down a very generic route like a data center, aggregate, or just a default route so that the spokes have a consistent path out of the network. The spokes don't need to learn all the other spoke routes because they all have the same next hop of R8 in this case anyway, so there's really no advantage to doing that. Assuming we have a solid EIGRP design, if R9 fails, yes, R8 needs to be notified through EIGRP and it will withdraw R9's prefixes. Assuming that R8 was doing redistribution into OSPF, it would be originating LSA type 5s, which are external LSAs, so R8 would have to withdraw that. The prefix isn't available over the WAN anymore, and R8 needs to tell the rest of the OSPF topology. That isn't a big deal because it's just a partial recalc. We're not dealing with any topology changes in OSPF, so no big deal. The most important thing is that there are no queries over the WAN between R8 and all the other spokes, like R10, so it's a very clean design that scales into the thousands without much effort. It's also important to consider what happens when the spoke comes back up. Ideally, when R9 comes up, it should send its new prefixes up to the hub, which will originate a new LSA5 into OSPF. However, downstream from R8 to R10, we shouldn't see any new prefixes being sent. This is because R10 already has a default route thanks to our hub-level summarization, and R10 already knows how to reach all of R9's prefixes as a result. There's literally no advantage in this particular design to send those prefixes down to every spoke. You'll just be wasting bandwidth, wasting time, and wasting compute resources on all the spokes. It slows down convergence, and it really has no business value. That's why EIGRP is so popular in large hub-spoke networks, because it works really well. Now, this isn't a talk on EIGRP. I just wanted to give you a high-level example for comparative purposes to OSPF. Let's take a quick look at the command line to see how EIGRP might work in this environment. We finally move into the WAN, and we're going to start on R8. I've enabled two forms of debugging. Debug IP routing will inform us about changes to the routing table, and debug EIGRP packets update will let us know when EIGRP update packets are sent. Now on R8, we're going to see these debugs executed because as the hub, R8 is going to have a lot of changes. I've also enabled these debugs on R10, and that's where we shouldn't see much output, if any. You can see I'm using tunnel 200 for EIGRP. Tunnel 100 is used for OSPF, which is the mainstay of this session, but for the demonstration of EIGRP, I added a new tunnel. You can easily switch between 100 and 200 to test different topologies if you like. We aren't going to talk much about it, but just know that both neighbors are up with no problems over tunnel 200 from the hub. Let's simulate a flap by going to R9. I'll use the clear EIGRP command shown so we can flap the neighbors and see how the network reacts. Let's go to R8 and see what happened. We're not going to scrub this entire debug output, but if we look at the bottom, we can see the highlights. It's clear that R8 and R9 exchanged update messages so that EIGRP could converge. R8 also had to update its routing table with prefixes from R9 like its loopback, so this is all expected. But what happened on R10? I've got the same debugs enabled and we see no output. The neighbor is still up with R8 and nothing changed. This is exactly what we want. We don't want R10 and all the other spokes to be notified every time another spoke goes up or down. The question is, how can we do this for OSPF? So we've been asked to use OSPF. Let's see if we can come up with a few simple solutions that might give us some improvement. The first thing that's probably on your mind is, let's change the area type to totally stubby or something like that. My question for you is, does that really help? There are some small advantages here. For example, we're not going to have any inter-area, type 3, or external, type 5, flooded into our specific area. So if there are other areas in the network, like from area 0 or other remote non-zero areas, or any external routes floating around, R8 is not going to originate them into area 2. That's good. Even better, R8 isn't even going to copy them into its local link state database for area 2, so you'll save a little bit of compute on R8 as well. The problem in our network, though, is that all the spokes, which number into the thousands, are going to share state with one another over the WAN. If you look at the diagram, R9 and R10 are still going to have routes for one another across this WAN, along with the inter-area default route that came from R8. Long story short, it is helpful and we are going to use it as part of our final solution, but by itself it is not sufficient to meet the specific constraints that we have. If we only use a totally stubby area, let's walk through what happens if a site goes down. If R9 fails, of course R8 is going to find out when it stops receiving hellos from R9, so the neighbor is going to fail as expected. R8 is going to flood a new type 1 LSA or router LSA to all the other spokes in the network. It basically needs to tell them I no longer have a point-to-point connection to R9 over this WAN. Because R10 received a new type 1 LSA from R8, there's been a topology change, and guess what? Every router in the area has to rerun SPF because of that change. If you have modern routers, maybe you don't care a whole lot about the SPF piece, but remember there is a lot of flooding over the WAN to communicate all this information. Now let's consider what happens when R9 comes back up. This is an even worse case from a flooding perspective than the previous one. Of course, R9 needs to run SPF as well because it was just added to the network. R8 has also seen a change. It has a new peer-to-peer relationship with R9, so R8 needs to flood its LSA1 as well to R10. Now R10 has to process both LSAs by running SPF again and determining all the paths through the network and ultimately installing R9's new prefixes that it learned inside of R9's LSA1. This might not seem like a big deal with only 3 routers, but if you can imagine these events at scale with thousands, it can become very chatty. For several years, I supported a US government customer that had huge OSPF-based WANs over DMVPN, and they made no attempt to optimize it. The OSPF flooding events over that network could literally bring the network to a crawl when critical applications would slow down while the network converged because a spoke somewhere else in the network had a flap. Before I show you the final solution, let's take a look at how this behaves on the command line. We're back on R8, except this time we're using OSPF inside of tunnel 100. We've got neighbors with both R9 and R10, and I've enabled a few debugs again. We're still going to track changes in the routing table, but we're also going to test intra-area SPF runs. If any changes are detected within area 2, we should get a ton of output from this debug. Let's quickly check R10. R10 has these same debugs enabled, and its routing table is here for reference. We clearly have an inter-area default route, which is expected, but we also have R9's routes. This is generally undesirable, and I'm going to show you why this is a bad thing. We'll go to R9 to simulate a flap. To do that, we use the clear IP OSPF process command. Because the network is so small, it converges pretty quickly, so let's go to R8 and look at the debug. Again, we won't scrub the SPF logs, but clearly we can see that SPF happened on R8. As the hub, we expect that to happen. We can also see that there were some routing table updates relating to R9's prefixes. Again, this is expected. But what happened on R10? For the most part, the answer is the same thing. R10 still got flooded with new LSAs and still had to run a full SPF within Area 2. That's highly undesirable, and it looks like our totally stubby design didn't completely solve that problem. A lesser known feature of OSPF is the LSA filter outbound that you can configure at the interface level. This prevents a router from sending any LSAs out of a link, period. None at all. You might be thinking, how does this even work? I mean, OSPF can't even communicate if it doesn't have LSAs, right? That's right, you're absolutely correct. It can't. The reason we would do this is we would only configure this on the hub, which would prevent the hub from flooding all those LSAs downstream when there are changes in the network. This will obviously solve a lot of the flooding problems, but we still allow upstream flooding so the individual spokes can dynamically tell the hub what prefixes it has. You might be wondering, how do the spokes know how to reach all the networks behind the hub? Just use a simple static route on the spokes that points up to the hub inside the DMVPN tunnel, and everything's going to work just fine. If you look at the diagram, it actually looks just like the EIGRP design we discussed a few minutes ago. The only difference is that the static route is static and not learned through EIGRP. This is advantageous because it mimics all the advantages of the EIGRP design except using OSPF. Let's examine what happens when one of our spokes fails using our new design. There's really only two things that are going to happen on router 8. Once the hellos stop coming and router 8 determines that router 9 is down, it will remove that neighbor from its table and rerun SPF. Even though R8 has generated a new LSA1, it doesn't have anywhere to flood it, so we don't have any flooding issues. Note that if R8 does have any kind of backdoor or alternative path to R9, it should try to use that. Assuming there are no backup paths, R8 will withdraw the summary LSA from Area 0, basically saying, okay, I don't have access to these prefixes anymore that came from R9, which is a simple recalc for the rest of the network. That's literally all that's going to happen with OSPF. There is no downstream flooding, and all the other spokes don't even know that R9 went down. They don't have any state for it. They're not even aware that R9 exists, and that's exactly what we want for scale. Now let's see what happens during the spoke up event. If R9 comes back online, there's a few other things that happen, but we still don't have any downstream flooding. R9 is going to come online and flood its Type 1 LSA to router 8, and of course R9 needs to run SPF because it is a newly joined router in the network. R8 will receive that Type 1 LSA from router 9 and of course rerun SPF because there was a topology change. This is the same as the previous case. R8 also has to re-originate any Type 3 LSAs into Area 0, so the 10.0.0.9/32 in our case will be re-originated into Area 0 so the rest of the network can reach this remote site. Again, there's no downstream flooding, no SPF on R10, basically no change on those routers, so this is how we achieve scale. In my experience, I was easily able to support several hundred routers to a single hub without a whole lot of problem and using pretty old hardware. Let's prove that this works how we think it should on the command line next. Back on R8, we still have the same debugs enabled so we can measure the impact. We still have both neighbors up with R9 and R10 over tunnel 100, so that hasn't changed either. The difference is that we can enable the database filter all out command on the tunnel, which prevents any LSAs from being flooded downstream. This feature also works for IPv6, and I've used both in production environments. Let's check R10 to see what changed. We still have the same debugs, but our routing table looks a little bit different. This time we have a static default instead of an OSPF inter-area default. That's because the outbound filter blocks all LSAs, so R10 would have no way to learn that over OSPF. The big advantage is that we don't have anything from R9 or any other spoke because those are filtered also. Let's simulate another flap on R9. Again, we can use the clear IP OSPF process command to do that. The neighbor comes right back up, but let's check R8 to see what happened. From R8's perspective, there's basically no change. R8 still has to detect the neighbor down, it still sees a change to R9's router LSA, and it still has to run SPF. It updates its routing table accordingly, but it does not need to flood those LSAs down to all the other spokes. Let's prove it by checking R10. Even with the debugs enabled, we don't see any output. Because there were no SPF runs and no flooding, there were no changes to the routing table, so there's nothing to report. If you're wondering how this is possible, let's quickly check the OSPF database on R10. R10 only knows about itself and no other LSAs. This is how you achieve scale in a hub-spoke environment, by hiding topology information within an OSPF area. Now, this isn't a DMVPN class, but I will show you how R9 and R10 have direct spoke-to-spoke connectivity even with this information hiding. Let's traceroute to R9's loopback from R10's loopback to see it work. The initial traceroute goes through the hub, and we can see 2 hops in the path. Because we have our routing table debug still enabled, we can see that there were some changes. The router installed a host route to R9's loopback via NHRP, which is what DMVPN uses for its control plane. We should have a new route in the routing table for this specific prefix with an updated next hop. See that new H route? That gives us direct access to R9 without having to go through the hub. We can confirm that with one more traceroute. Of course, I have to type it correctly for it to work, so let me try that again. Okay, clearly it's taking only one hop now, and it's going directly to R9 instead of through the hub. The reason I'm showing this is that you can still get optimal routing and scalability with this design. Again, I've used this a few times in production, and it works really well. Some of you might be wondering, well, since we're doing static routing, how can we have multiple hubs? That makes the upstream routing a little bit difficult. This is conceptual, and we're not going to set this up because it's a little tricky, but we can use Anycast to solve this problem. Suppose you have 2 hubs, H1 and H2, and maybe they're connected to different transports like MPLS or internet. If both routers have a common tunnel source and they advertise that into their provider networks in the underlay, then the tunnels are going to form to whichever hub is closest. If one of the hubs fails, like in our case where H1 has failed, S1 and S2 will redirect their tunnels to H2. Yes, this is a convergence event. There will be an outage. The IPsec tunnel needs to reform. The NHRP registration needs to happen again. The OSPF neighbor needs to come back up. So it is a bit slower than if you had both neighbors up at the same time. This is one of the trade-offs of using OSPF in this manner, but in my experience, this does work well. I've deployed this exact design in production across many continents, and it's been working great for several years. I even wrote a free professional white paper that explains how this design works and how you can replicate it. I'll provide a link to that at the end of the entire session, and you can check that out if you're interested in learning more about scaling OSPF over hub-spoke networks.